Okay, so this video is going to go through something called Le Chatelier's principle. And I want to define it first. So Le Chatelier's principle states that if a stress is applied to a system at equilibrium, the equilibrium position will shift in a direction to reduce or counteract the stress. Your book talks about it a different way. It actually talks about different kinds of stress, which we'll get to in a minute. But it talks about how if a system at equilibrium is disturbed, the system will shift its equilibrium position so to counteract the effect of the disturbance. So a good example of this is thinking about a screaming baby. So you're babysitting and everything's fine, and then all of a sudden this baby starts screaming and you have absolutely no idea why. The stress would be the screaming baby. The system at equilibrium would have been you and the baby and things going fine, and then all of a sudden the baby starts screaming. So that's the stress. And what's going to happen is you are going to do everything you possibly can to get that baby to stop screaming, which is like the reaction shifting in one direction or the other to counteract that stress. Now in chemistry, there's going to be 3 different types of stress that we are going to look at. And the first type of stress is going to be a change in concentration. So you're changing the concentration of one of the reactants or one of the products, and then looking to see which way the reaction is going to shift to reduce or counteract that stress. A change in volume or pressure. Typically, the way this is going to be worded is giving you a change in volume of the container, and then you're going to have to think to determine what the change in pressure would be. And then the third type of stress is going to be a change in temperature. So these are the 3 major types of stresses, and we're looking at, should have made this bigger so you could have seen it bigger the whole time, but we're looking at which direction the reaction is going to shift to counteract those stresses. So the first thing we want to do is we want to look at a change in concentration. And I want to start by looking at a balanced chemical equation. And we're going to use nitrogen plus 3 moles of hydrogen is going to give us 2 moles of ammonia gas. And so the first thing I'm going to do is I'm going to add nitrogen. So I'm going to increase the amount of nitrogen that I have. So that's the stress. Now when you add a reactant, what that does is there's more reactants available. So the reaction is going to shift to the right to produce more products. So if you add a reactant or increase the concentration of a reactant, the reaction is going to shift to make more products. So what's going to happen is that your concentration or pressure of ammonia will increase. Now the same thing would happen if you increased the concentration of hydrogen. If I increase the concentration of hydrogen, I'm stressing the reactant side, so the reaction is going to shift to make more ammonia. Now what happens if we do the opposite? Let's say we're going to add a product instead. So in this case, we're going to increase the amount of ammonia. What that's doing is that's stressing our products. So the reaction is going to shift left to make more reactants. So 2 directions that the reaction might shift depending on your stress. Okay, so now what we want to do is we want to look at what happens if we reduce the amount of, I guess I'm going to get rid of this, and I'm going on to the next page. So, same reaction. Now what we want to do is we want to look at what's going to happen if I reduce the amount of a reactant. So let's say I just get rid of nitrogen. So what has happened is our amount of nitrogen has decreased. That stresses the reactants, or that stresses the reaction. So because I removed or I decreased the concentration of a reactant, so the reaction is going to shift left to make more reactants. Same thing's going to happen, or the opposite will happen, if I'm going to add nitrogen back in. Okay, and so now this time what we're going to do is we're either going to decrease the concentration of our ammonia, or we're just going to remove it. And so when that happens, that stresses the equilibrium again. The reaction wants to shift right to make more. You could think about this as like the problems that we did where we had 0 on the product side, and the reaction wants to shift that way to make more of it. So if you remove or decrease the concentration of a product, then the reaction is going to shift right to make more product. So that's what happens when we have changes in concentration. I also want to mention that you need to think about the initial shift. You don't want to think about subsequent shifts. So all we're asking is when this stress is applied to the system, what's the initial shift, not what's going to happen after that initial shift. All we're looking at is the first shift. Okay, so our next one, I don't know why this slide is here. Okay, change in volume or pressure. That's our second kind of stress. So this is going to be a little bit different. If the pressure increases, so okay, so sorry about that. If the pressure increases, the system shifts to decrease pressure, and it's going to do that by moving or shifting to the side of the reaction with fewer moles of gas. So if pressure goes up, the system wants to decrease that pressure because it doesn't like that stress. So it's going to do that by moving, I'm sorry, I keep doing that, to the side of the reaction with fewer moles of gas. Now, in the opposite situation, if pressure decreases, that's the stress on the system. The system tries to increase pressure by shifting to the side with more moles of gas. So when you're doing problems like this, you need to pay attention to how many moles of gas do I have on each side of the reaction. And if you have something that's a solid, you don't consider it. A solution, you don't consider it. So let's see, let's just pick a situation here. Okay, so what we're going to do is we're going to take this system that is at equilibrium and we're going to stress it by decreasing the volume of the container. So we decrease volume, so that means that pressure is going to increase. So because pressure increases, the system tries to decrease pressure by shifting to the side of the reaction with more moles of gas. Wait, I said that backwards. Hope you guys caught that. We're trying to decrease pressure, so we're going to shift to the side with fewer moles of gas. Okay, so in this situation, if I look, I have a coefficient of 1 here and I have a coefficient of 2 here. So in this situation, it's going to shift left. So that would mean that our concentration or pressure of dinitrogen tetroxide would increase. Okay, now let's look at what happens when we increase volume. So in this situation, this equilibrium here, we're going to increase volume of the container, so that will cause a decrease in pressure. That decrease in pressure is a stress on the system. So the reaction shifts to increase pressure by moving to the side with more moles of gas. Okay, and in this case, I'm going to have 3 and 1, so that's going to be 4 moles of gas on the reactant side. I have 2 moles of gas on the product side. So in this situation, it's going to shift left to try to increase pressure. Okay, now there is a special situation where on a question, you're going to be asked about adding an inert gas. And typically those inert gases are going to be like noble gases. The important thing is that those, the gas that you add will increase the total pressure in the container. But by adding that gas, let's say we add something like argon or helium, by adding that gas, it doesn't change the partial pressure of any of the individual gases that are already there. It's also not included in the equilibrium expression because it's not participating in the reaction. That's what's important about being inert or non-reactive. So you need to watch out for questions like this, because they'll ask you the direction of the shift when you've added an inert gas. And what you want to say is that adding an inert gas will increase pressure, but it has no effect on the equilibrium position because it's not included in the equilibrium expression. So you're basically saying that there's no shift in direction. There's no effect on the equilibrium position. Okay, so we've looked at change in concentration, we've looked at change in volume. Now what we want to do is we want to look at change in temperature. Now if you remember when we were introducing you to the equilibrium constant, we talked about how equilibrium constants were a value that were constant unless temperature changed. And the reason that they would change with the change in temperature is because pressures or concentrations were part of the expression, and both pressures and concentrations will be affected by a change in temperature. So when you have a change in temperature, that will change both the equilibrium position and the value of the equilibrium constant. So what we want to do now is we want to look at what's going to happen to the direction of the shift. The direction of the shift is going to depend on whether the reaction is exo or endothermic. And so rather than having you memorize a particular pattern, what we're going to ask you to do is we are going to ask you to physically add the word heat to the reaction as a reactant or a product, and then to treat heat as you would a change in concentration. Okay, now some of you are not going to want to do this because you're going to actually have to add 4 letters to one side of the reaction or the other, but you need to do it because this will make it very simple to figure these out. So you want to physically add the word heat to the reaction as a reactant or a product, and then treat heat as you would a change in concentration. So let's look at this. 2 different examples. Reactants on the left, products on the right. The first example, we have a positive delta H. So because we have a positive delta H, we know that this is an endothermic reaction. And if it's an endothermic reaction, it's going to require energy. So heat is going to be a reactant. So when I say physically add it, I mean write it in on the reactant side. The second example is negative. So that means our delta H is negative. So it's an exothermic reaction. Exothermic reactions generate heat. So you are physically going to write in heat as a product. So that's what I mean when I say physically write it in. So now let's look at some examples. Okay, so the first example, and this is how you're going to see it on the exam. You'll be given a reaction, you'll be given a delta H. Sometimes they'll tell you exothermic, endothermic, but most of the time you'll be given an enthalpy and you'll have a positive or a negative sign. And so I know that because this is negative, it's exothermic. That tells me that heat is a product, so I'm going to physically add it to the reaction. Now what I want to think about is what's going to happen when I change temperature. So let's say I increase temperature. That means the amount of heat is going up. So the stress is increasing temperature, increasing the amount of heat. The reaction doesn't like that, so it's going to shift to the opposite side, which means it's going to shift left. Now, if you think about forward and reverse reactions, the reverse reaction, as it's written, has heat as a reactant, which means that increasing temperature is going to favor the endothermic reaction. Oops, sorry. Okay, now let's say we change that. Still an exothermic reaction. So heat is still going to be a product. But what we're going to do this time is we are going to decrease the temperature. So decreasing the temperature is going to stress the reaction. The reaction is going to shift right to try to make more heat. So decreasing the temperature favors the exothermic reaction because this is going in the direction that produces heat. So let's look at another example. In this situation, we've got PCl5 as a gas in equilibrium with PCl3 as a gas plus chlorine gas. Our delta H is a positive 87.9 kilojoules. So the first thing we want to do is look at our delta H. The delta H being positive tells us that it's an endothermic reaction. So I know that heat is a reactant. So I am physically going to write heat in as a reactant, and then I'm going to answer all of my questions with the reaction this way. So let's say the first thing we do is we are going to increase temperature. So if we increase temperature, what that means is that we are increasing the amount of heat. If we do that, that's going to cause the reaction to shift to the right. So increase temperature, reaction shifts right. Favoring the, okay, if I look at how the reaction is written, going in the forward direction, it's endothermic. So I'm going to say it's favoring the endothermic reaction. Okay, let's do the opposite now. Let's say that we decide that we're going to decrease heat. So that's kind of like decreasing temperature. So what will happen in this situation is the reaction shifts to produce more heat. So the reaction is going to shift left to produce more heat, favoring, in this case, the reverse reaction, sorry, And if I look at the reverse reaction, it's generating heat, so it's favoring the exothermic reaction. Okay, so what's really happening here, the way that we write it, is the reaction is shifting to either make more or consume what's added or what is taken away. So if you add something, it's shifting in a direction to consume it. If you take it away, it's shifting in a direction to produce it. Now, there's one other thing that I want to talk about, and this is the effect of a catalyst on an equilibrium position. And what you need to know here is that the addition of a catalyst will increase the rate at which equilibrium is achieved, but it does not affect the equilibrium position. So let's look at why. And that can be an actual answer that you would include if you're asked about this. So if you think about our activation energy curves or our energy diagrams, and I'm going to draw an exothermic one. So this will be our energy diagram. We're starting with reactants here, going to products here. If you remember, the difference in energy between reactants and products is our delta H. And then the height of the hill from reactants to the top of the hill is our activation energy. Now, when we add a catalyst, and I'm going to make the catalyst pink, what happens is it lowers the activation energy by providing a new pathway. So it doesn't change the delta H, doesn't change the energy of the reactants or the products, but it provides a new pathway with a lower activation energy. So now, if I look at the forward reaction, it doesn't change the equilibrium, but the catalyst increases the rate of the forward reaction because doesn't require as much energy to get to the top of the hill. So now if I want to look at the reaction in reverse, so I'm starting here, but now instead of having to go all the way up here, the catalyst has also lowered the activation energy for the reverse reaction. So the catalyst decreases the activation energy for the reverse reaction, and what that does is I'm sorry, I wrote that backwards. By decreasing the activation energy, it increases the rate of the reverse reaction. So it doesn't affect the equilibrium position, but it does speed the rate at which equilibrium is achieved. And that's pretty much all you need for Le Chatelier's principle. I'm going to do a separate video for how we do calculations with Le Chatelier's principle.